Hi guys, if you don't know me already, my name is Mara Keller, and I'm going to be talking about some of the methodology in a paper published by Stephen Lavington and Anthony Watts. And just to give them credit, the title of the paper is Detergent-Free Solubilization and Purification of a G protein coupled receptor using a PMA polymer. And specifically in this presentation, I'm going to be focusing on the dialysis protocol. So let's get right in. So here is the abstract of the paper just for your guys' general reference, just so that you can kind of see the researcher's perspective on the whole methodology. So kind of to get into the paper itself and give you guys a general overview of the paper is a GPCR. As you all know, we all took cell and molecular biology if you're a biochem major like me. GPCRs are very important cellular receptor proteins. And they're actually transmembrane proteins. So they contain some hydrophobic regions and also some hydrophilic regions, which allow it to be able to interact with the lipid bilayer. So normally when isolating these transmembrane proteins, it's a little bit difficult because you're not only separating the protein from just normal cellular debris, you also have to actually extract the protein from the lipid bilayer. So how this is done commonly now every day is people use detergents, and as you guys probably know, detergents are amphipathic molecules, so they actually have a hydrophobic region as well as a hydrophilic region, and these substances are really important because they have the same similar amphipathic properties as the lipid bilayer. They are actually able to go in and disrupt the lipid bilayer, allowing for the transmembrane protein to be extracted from the membrane. However, because these detergents can go in and disrupt these intra or intermolecular bonds from protein to proteins, and protein to lipid bilayer, they're actually pretty good at also disrupting the tertiary and secondary structure of proteins and those intramolecular bonds actually within the protein. And as you guys know, if you denature protein structure, then you a lot of times lose protein function. And GPCRs are really important proteins that are analyzed because of their function. They're involved in a lot of cellular pathways that can involve cancer and other cellular diseases like that. So it's really important that we're able to analyze these proteins on a functional level, and also keep their native structure for that to be analyzed as well. So in this paper, they hypothesized that a polymethacrylate polymer, PMA polymer, could be a strong alternative to traditional detergents for solubilizing transmembrane proteins. So they hypothesized that using this to dissolve transmembrane proteins will actually preserve protein function. So here you guys can see the structure of a detergent. And if you notice, while we have, the normal head and tail group like we see in the lipid bilayer, there aren't two polymer tails here. There's only one. So this kind of gives it an overall cone structure, allowing it to form these spherical structures in solution. And this is actually why they can disrupt the lipid bilayer. This is actually pretty similar to what PMA, the alternative, looks like as well. It's just not as strong to actually go in and disrupt those secondary and tertiary interactions that we want to keep intact for protein function. So here's the overall purification steps of the paper. The paper actually went into a lot of depth on a lot of different levels of this. So this is simply the purification methodology, but if you're interested in knowing more about what they did to test solubilization and more stuff like that, you can let me know and I can send you the paper. But so for the actual protein purification, they did a lot of centrifugation. They did it a couple times just for major separation of cellular debris. And then they actually did a nickel immobilized metal affinity chromatography for further protein separation. And then the step I will be talking to you all about, dialysis for the cleavage of the green fluorescent protein tag and separation of small impurities in solution. And then after dialysis, they go on to the cleaved protein applied to anti-flag affinity chromatography for further separation. And then finally, they applied the protein sample to SDS page for further purity analysis. So just a little bit on dialysis. So generally, dialysis is a tool employed for the separation of small molecules from larger macromolecules in solution. This is really important. As you guys know, we've all taken Biochem lab, or you're probably in it now if you haven't already taken it. And we do a lot of dialysis in those procedures because they are really important for removing those smaller molecules that centrifugation maybe can't separate. So dialysis relies on the principle of selective and passive diffusion through a semi-permeable membrane. And the components of dialysis are a protein sample solution, of course, a buffer solution, and a semi-permeable membrane with appropriate molecular weight cutoffs. So how this works, the procedure of it is, and you guys have probably seen it in lab before, there is a semi-permeable tubing, just a round clear tubing, cylinder shaped, and you pour your protein sample solution into that, and then let it dialyze overnight, or however long the procedure calls for. And that is something else that's really important to touch on for dialysis. The specific components and the specific details of a dialysis experiment is really going to depend on the protein of interest, because dialysis membranes are actually sold based on their molecular weights and what molecular weights can pass through and what molecular weights can't. So you need to make sure that you know the target molecular weight of your protein so that you don't accidentally lose some of your protein that you're trying to extract out of solution in dialysis. So normally, and also with that, people can do dialysis procedures over and over again. They can be done in conjunction with other procedures because they're very simple. And the temperature at which a dialysis procedure is performed is also very much dependent on the protein of interest. I know for a lot of protein samples, if you're worried about degradation or other things like that, they'll normally be done at 4 degrees Celsius. However, the colder it is, of course, the longer it will take. So these are all things to take into account whenever you're doing a dialysis solution, is you want to make sure the conditions are prime for your sample solution. So applications of dialysis is such a simple purifying procedure that it can really be done in conjunction with most protein purification procedures. You normally see it done in conjunction with chromatography. normally before chromatography is done, just to remove, again, those small molecules from solution that could interfere with your column. Um, and then just going into dialysis in this specific paper that I'm talking to you about. So this paper, before they actually did protein purification, they started by testing if PMA could even solubilize GPCR. So they from solution or from the membrane. Um, so in order to test for this, they actually tagged the GPCR of interest with a green fluorescent protein, like we've talked about in class before. And then they did some spectrophotometer experiments to check for their protein in solution to ensure that the um, solubilization was successful. So the solubilization was successful. However, they wanted to make this protein sample as pure as possible. So to do that, they needed to remove that green fluorescent protein tag. So that's the sample that we're starting with. Is we're starting with our sample protein with a green fluorescent protein tag. And actually in dialysis, the buffer solution used in this experiment, they didn't go into extreme detail of exactly what type of buffer solution was used. However, they did do this dialysis in conjunction with cleaving the green fluorescent protein off of the transmembrane protein. And like this is what I said before, it's really easy to put these dialysis procedures in conjunction with other ones. So while they were um, putting the HRV3C protease in their sample solution for the green fluorescent protein to be cleaved off, they also were dialysizing. So just removing, again, all of those small impurities, think ions, think small pieces of cellular material, and things like that. So the results of this methodology in the experiment, it successfully removed the small macromolecules or the small molecules from solution. And we know this because an SDS page gel was ran to check for purity. And the green fluorescent protein was also successfully cleaved. And then after dialysis, the sample was then applied to further chromatography to actually remove the free green fluorescent protein from solution. So now, just for some overall highlights, so just some general things to take from this is dialysis is a really simple, short step in a purification procedure that can really help your purification results with proteins. It's super easy, it's super simple, it can be done overnight. And really all you need is some buffer solution and a semi-permeable membrane that is selective for your protein. So the final results actually of the overall paper, just to give you guys kind of a wrap up on that, is they did find that PMA polymers were successful in not only solubilizing GPCRs from the lipid bilayer and solution, but also for preservation of protein function. They actually found that the proteins that were solubilized with PMA had significantly more activity than ones solubilized in detergent. However, further research still needs to be done on these practices because protein yield was very low for the proteins that were solubilized in PMA as opposed to detergent. However, there was some sample loss throughout the experiment, so that is what the researchers attributed that to. But yeah, that's all I got for you guys. Thank you so much.